Alright guys, so today we're going to have another recap on the VCdimension, and then we start your new topic, bias and variances. We're going to carry on this topic for 3 sessions, and then your final topic for this semester would be SVMs, which will start in a week or so. So, if you recall, last session we talked about how we're going to use VCdimension for a linear classification case, for which you have a perceptron that accepts your data set from your x's, which are R, from D plus 1 dimension of R space, and then it's going to output either plus 1 or minus 1, right? So that's a classic perceptron. So we also talked about using VCdimension in order to find the complexity of a perceptron model, right? Because before that we were using Hoeffding's inequality and then union bound, and we talked about M as a weak generalization for model complexity, and then we came up with the growth function, right? And then we said that growth function could be up to 2 to the raise of n, for which we call it shattered. And for several cases, it was smaller or equal than 2 to the raise of n, given the constraint we would use on the combination of the dichotomy set, right? We had an example in the previous lecture that you had 3 x's, so 3 points. So in a sense, they could have gone up to 8 dichotomy set, right? But since we constrain using a growth function that each of the individual 2 cannot have more than 3 combination, this reduced to 4. All right? And then we try to analyze the linear classification. We came up with this 2, and then we had the proof, right? So we said n, if n is smaller than or equal to d plus 1, then there exist n points that are shattered, and then d plus 2 is a breakpoint for h. That means that we don't have, this is going to be the upper bound of the complexity, right? Can anyone tell why? We talked about it last session. So why n equal d plus 2 is a breakpoint for h? As you recall, we had d plus 1 parameters of w, thus we had d plus 1 parameters for x's, right, here. So can anyone tell us why n equal d plus 2 is a breakpoint? We talked about it in the last session. Any guesses? So in general, in a linear system, because this is a linear classification, right? Each of these x's represents a vector. That's why we present them this way, right? Each of the x's, starting from x0 to xd, thus they are d plus 1. Each of them are representing as a vector, right? 0, 1, like 1, 0, and then 1, 0, 1, right? And these are equal to the result of this, right? All right, so now we have d plus 1 linear systems in your algebra, or yeah, I guess it should be algebra. When you have more parameters than your linear system, you have d plus 2, and then you have d plus 1 here, linear systems. So that means that at least one of the vectors are dependent with the others. That's why we cannot find the result, find the value of all those d plus 2 values. That's why d plus 2 is a breakpoint. You can't expand it more than that. So we have d plus 2 points as our parameters. We have d plus 1 samples, right, x's, as our linear systems. So obviously, this linear system cannot be solved unless one of these, at least, are dependent, right? So the number of parameters are more than our linear system, so the number of lines. So one of these are dependent. That's why d plus 2 is the upper bound and is the breakpoint. Another intuitive sample, like you have 2x plus 5, y is 3z, right? It's 2. And then you have 4x, 4y, 4z is 5. You have 2 linear systems, 2 lines, and 3 parameters, x, y, and z. Can we solve this? We have 3 parameters, x, y, and z, and we have 2 linear systems here, 2 vectors. Can we solve this? That's right, we cannot solve it because at least one of the parameters, either x, y, or z, can be written as a dependent on the other two. That's why we can't solve this. If we had another one, the third line, another linear system, we would be able to solve it because it was 3 by 3. Just like this case here. We have d plus 2 points as a parameter, so our parameters are 1 more than the linear systems. That's why at least one of them are dependent. So that's why d plus 2 is the breakpoint. As you see, these are the vectors, so each of them could be represented as a vector of binary values is a linear classification, right? Thus, at least one of the vectors can be defined as a linear combination of the others. And this is also, if you take a look at your textbook, Learning from Data, at page 103, it briefly mentions the higher orders and the VC dimensions related to that. So if we expand this linear system to a higher order, second order or third order polynomial, what's going to happen to the VC dimension? If you need more resources on that, you can just refer to the Boyd's textbook, or just Google online. There are multiple statistical, references out there for that. So now, that was the case for the linear classification. We also talked about using VC dimension for higher orders, like second order or third orders. So, in general, using this transformation Z, we can generate a second order polynomial, right? Which has this sort of shape, right, instead of a linear case. So what's going to happen to the VC dimension of a higher order, such as this, a second order. We briefly mentioned in my last slide, last session, that the VC dimension of H would be equal to 6. So there are, and we didn't give any proof. I just stopped the course at that point. So there are multiple ways to see why the VC dimension is going to be equal to 6. One way is to draw 6 points, a 6 by 6, and see how many hypotheses you can generate using a dichotomy set. The other point is generate a 6 by 6 matrix and then get a rank of that matrix. So always rank of the matrix of 6 by 6 would be this. You can use MATLAB or Python as well. There are also proofs out there that are outside the scope of the course, but you should know that when the orders go higher, VC dimension also increases in a polynomial way. So again, for this, yeah, I just put the reference page here if you wanted to have a look, page 103 in the textbook. So in order to see that why VC dimension of the second order is equal to 6, so you have a quadratic transformation, z or phi here, that does this transformation for you, right? 1 and x1, x2, x1 square, x1, x2, and x2 to the raise of 2, such that it does a transformation of z, right, given this. So now the price we pay by this transformation is that it generates a 5-dimensional 5-dimensional instead of 2-dimensional, because this is a first order. You can generate using I would call it Z1, and this is Z2, right? The second order, just per se. So the price we pay for having a second order is that Z is a 5-dimensional instead of a 2-dimensional. And thus, your VC dimension is doubled from 3 to 6. This is one way to see that the textbook was describing on that page. Also, an easier one is just use the function that returns the rank of a matrix. A matrix so the maximum number of independent rows or independent columns in a matrix. So you have a matrix. These are the rows. These are the columns. The maximum number of independent rows or independent columns will represent rank of a matrix. How are you going to count the independent rows? There are also statistical ways. I mean, I just don't want to point them out. You can just have a look at them yourself. But this is another way. The second method normally you can use is using a rank of a matrix. So this is first order. So make Z1. This is second order. So like if you have a simple matrix like this, like 2, 4, 6, like 2 rows and 3 columns, and the second row is 1, 2, 3, right? Definitely this matrix has a rank. If you take a look at the rows, the second row and the first row are linearly dependent because it's just a multiplication of 2 of each of the elements, right? So definitely if you get the rank of this matrix, definitely it won't be 3, which is the highest number here of the row columns. It might not even be 2. So this is one example that the vectors or columns are linearly independent. Linearly dependent, actually. I left also PowerPoint again. Yeah. All right. So now, let's apply the same thing instead of classification to our regression problem. So the difference is here, now we have to deal with real values, right? Instead of the binary values. So definitely it's going to expand the problem. Let's see if using VCdimension is a good method to analyze the complexity of such model. So as you recall, we already talked about the loss function or squared error in linear regression. Thus, the in-sample and out-of-sample error for the candidate hypothesis of G can be calculated as 1 over n, the summation of i's from 1 up to n. The difference so is just a simple square error. All of those values that your hypothesis G estimates or predicts minus the real values square, and also your test error would be the expected value of the y minus g raised to 2, right? So if you take a look at VCdimension in this case, you see that VCdimension approach is not directly suitable for such a model. Why? Because unlike the binary case in the classification, it's not easy to come up with the number of hypotheses that you can shatter your training set because they're real valued. So what you can do at most is use VCdimension, so the VCD of a class of real valued function, such as our case in the regression model, when you have a g of x and a, is defined to be the VCdimension of the indicator class, the indicator function of gx of a minus beta greater than 0, where b takes values over the range of g. So that's a reference for that. And the issue with this is VCdimension, instead of getting the complexity of the class, it can get the complexity of the indicator of the class, the value of the threshold instead. So instead of the class, instead of the model, it's going to give you the value for the threshold of the regression, right? Threshold. If you recall for the bank application, so we would find a threshold that below that threshold, for instance, the credit card application would be rejected, and above that it would be accepted, right? That's why we call this that is not directly suitable because it's not directly able to get the upper bound of the complexity for the regression. Rather, it could get the complexity of the threshold value. So what else we can do instead? Because we're talking about real values in regression, instead of going for VCdimension, we are defining two more statistical values, such as bias and variance, and we're going to use this in order to, compute the complexity of generalization bound in regression models. If you click on this, it's going to bring you to that specific page of the PDF if you wanted to have another reference for that. Okay. So as I mentioned, VCdimension, it gives you the VCD value for the threshold indicator instead of the real model. That's why we call it is not directly usable. You can use it as a proxy to find a class. Also, just like the previous case, normally in practice, if the number of your n would be around 10 times the dimension, we say it's a good rule of thumb for avoiding the overfitting problem. All right? So now that we see VCdimension is not a good tool to understand the complexity, let's talk about bias and variance in this couple of lectures. Okay, so let's define bias and variance. So these two parameters give us a trade-off, and then we define bias as how well can we approximate the unknown function f using hypothesis h, right? So that was your unknown function f, and as an example, this is your hypothesis g, the candidate from your capital H, the set of hypotheses. You see, at some point it's trailing sort of fairly well your unknown function, right? So using bias, we can say how well can we approximate this unknown function. How about variance? So variance, by using variance, we say how much does the output G change as we vary the training set D, right? So we are interested in the changes now. So now we use these two parameters in order to estimate how well a prediction model is. All right, so let's see an example for this. We're going to start with the first example. Assume your hypothesis was a constant hypothesis, just a line in a 2D word. And your unknown function was pi x. So the sign of pi x. Our range is from -1 to +1. So if you draw that unknown function for the given data set, x0 and y0, so we call it with this notation g of d of x is equal to y0. So d is a superscript of g. We show it this way. So example number 1, we have h as a constant hypothesis, right? It defines a line, say it is C. So the x's, there are only one from each hypothesis, x0, and they're coming from a uniform distribution of -1 to 1. Thus, y0 is equal to f of x0, right? So if you draw this is your f of x, which was unknown, which was sine of pi x, in the range of +1 and -1. We are trying to understand if we use a constant hypothesis. In this case, we use these two cases. And each of them has 1 point. So these blue lines, this blue line for the g of d2x hits the value of the unknown function, this point. The second, the first one shown in green, g d1 of x, is the sine pi x, this point, right? So these are two constant hypotheses. So what can we observe from these two simple constant hypotheses? You see that if you use, so we are interested in using bias and variances to describe this, right? Let us define g bar of x as the expected value over the data set D of this g of d of x. In this case, you see that at those 2 points, one for each, the expected value of the test is 0, right? Because they actually hit it. So if you use bias or variance, you're going to have g bar x minus f of x squared. And for the variance case, you're going to have expected value of d gdx minus g bar of x squared. And if you compute that, it's going to be 1. So this is a very small and easy example to see that by using bias and variance, you have more flexibility to just go for the real values. Okay, so now let's have another example where our hypothesis, instead of a constant, is a linear case. Okay, we have the same unknown function. Instead of a constant, we have linear, and the linear passes through the origin point, which is 0, 0. So what's going to happen this way? We have 2 again, shown in blue and green, gd1 of x, d2 of x, and they are passing through the origin point, which is 0 here. And we have 1 points from each, here and there. In this case, if you compute the g bar as the ed gdx, it's going to be sort of around 185. And you see that the bias varies here. They are the largest at two extreme points, +1 and -1. And at 0, because these are passing through the origin, which happen to be the passing point for the unknown function, thus the bias is 0, right? So we have a bias of 0 at origin and maximum biases at the two ends, -1 and +1. Is it clear? Here, 0. These are the largest here. Okay, so let's generalize more. What if we have other type of hypothesis? So we already talked about a constant one and a linear case. What if we go for an advanced and more complex hypothesis? What's going to happen in general to bias and variance? So the third example, what if you have a complex hypothesis? All right, so in general, if you go for a more complex one, so in higher orders per se, like instead of a linear, you go for such as this, right? So more complex one. In general, your G bar X is a good approximation because say this is your G. Suppose that was your F. Like that was your F. It can trail your F in a better way if you have up and down in your data points of F shown in dash. So the dash line is assume that was your unknown function of F, and this is your G. So it gives you a better approximation of your G, approximation of your F. Thus, your variance is going to be smaller, right? At each point, it's trailing the dash line much better. I'm sorry, your bias is smaller, but usually you have large variances because at some point you have a perfect point like this. At some point you have a high differences. Again, at some point you have small. At some point you have high. Right? So the variance, these changes are very high. Right? This is in general the case for using a complex hypothesis. On the other end, what if we use a very simple hypothesis, just like the one you saw in the constant case? Suppose your G would be a complex shape like this. Suppose your F would be as complex as this, and you had a G dash line like this. Very simple, right? So you see that it's a weak approximation of your F. You have large bias, but a small variance. the opposite case for a complex one, right? I'm just gonna stop here at this point, and start fresh next week with a recap of these bias and variance, and we go further with that to define the complexity of models for other type of models we saw here. Any questions? All right, guys. Have a good day.